Dante Certification Level 3, 2nd Edition. Layered Network Models. Before Audiante had the Dante certification program, many early adopters of Dante would rush out and take a networking class at their local community college. Of course, they'd come to us with their questions, right? Well, one of the topics that came up a lot was the OSI model. And over time, I think we eventually came up with an explanation that worked well for AV professionals to understand this concept. Let's see if this helps you. The OSI model breaks down communication into 7 layers, describing how different functions work together. According to Wikipedia, the Open Systems Interconnection Model, that's the OSI model, is a conceptual model that characterizes and standardizes the communication functions of a telecommunication or computing system without regard to its underlying internal structure and technology. Is anybody feeling any smarter than they were before we read that? That's a lot of concepts all jammed into one sentence. Let's break this down for you. First, the OSI model is a conceptual model. I think many AV professionals get excited when they hear about the OSI model. They expect it to be like an owner's manual to Ethernet. And it's not that. A model like this is intended to speak without regard to the underlying internal structure and technology. So the OSI model does not offer great detail on how a network operates. It intentionally stays very generic. If you're looking for excruciating detail on a protocol, you're going to have to go to the documents for that particular protocol. Now, just to see how we would apply the OSI model, let's use it to describe a familiar process of writing and mailing a letter. You start by writing a letter. Well, that's a combination of the top 3 layers. In the OSI model, that might be a combination of Microsoft Word, the Windows OS, that sort of thing. Eventually, that letter represents your data, and you put it in an envelope. In networking, that envelope is called a datagram, and that's layer 4. On that envelope, you put the to and from addresses. On the network, we put that in MAC and IP form, both for the transmitter and the receiver. And that brings us down through layers 2 and 3. Finally, the letter will travel to another destination with the mail carrier, on trucks, and so on. That's the physical layer, layer 1. So the OSI model is a helpful way of visualizing the system, whether you're designing, configuring, or troubleshooting. For instance, let's suppose the mail carrier couldn't read the recipient address. You'd say, that's a layer 2 or layer 3 problem, and you can start developing solutions for that. As opposed to the mail carrier's truck broke down. That would be a different set of solutions, right? So let's do this again with a network. In a computer example, we might have something like a digital audio workstation, a conferencing application, Dante virtual sound card. All of that will create some data for our network. That's a combination of layers 5 through 7. At layer 4, we put that data in a datagram. At this point, we're adding information about the protocol that the packet will use. For Dante, most of this will be UDP, and we'll add the source and destination IP ports that this will communicate with. Again, the IP port is the number that follows the IP address, separated by a colon. Layer 3 adds the source and destination IP addresses to the datagram. This might be where you're considering your subnet and determining whether to address the device directly or to contact the gateway. When we get down to layer 2, we add the MAC addresses. Here we look in our ARP tables to find the MAC for each IP, and of course if we don't have them, then we use an ARP who has request to resolve that, right? Finally, when the packet is assembled, layer 1 refers to the physical hardware. So the electrical levels on the cable, the light in the fiber optic cable, the type of cable itself, all of that. So you might look at something like this and say, oh, I get it. So switches are layer 1. They're physical things. And to an extent that's true, but the transmitter that you had was also a physical device, and we didn't have a problem seeing the logical layers in there, now did we? So when a switch receives this, that's physical layer, and then it comes up and says, okay, I need to look at the MAC address to know where to send this. When it's doing that, that's layer 2. If we're in a router, we're up at layer 3 because we're looking at the IP address and saying, where do I need to send this? So we'll go through those things, but understand that devices will start at a level, They come down, make it a physical transmission. That goes to a switch, which then has to go up the stack to some extent, come back down, send it physically to another device. And so you'll visualize this going up and down the stack over and over again. And of course, once the packet arrives at the destination, that device will unpack this a layer at a time. We convert that electrical signal to logic. We'll see the message came from a MAC address which had an IP that used a protocol on a particular port number, and we'll give that data back to the BIOS, the operating system, and the applications that want it. It's certainly true that I blur those top layers of the stack quite frequently. If we're a programmer, we're going to be very interested in those top layers. That's all important for them. But as a network engineer, most of your work is done in the bottom 3 or 4 layers. You don't really care what generated data, you just know that you received some and it needs to be transported to someplace else on the network. Realistically, this led to other models like the TCP/IP model. If you line that up with the OSI model, we'll see that some layers get combined, and that sort of reflects the idea that we need more detail in the area that we're working. We don't need so much detail in the other areas. Ultimately, the OSI model is interesting because it's used across professions, and it still gives us enough detail in the areas that we need to get our work done. So for the purposes of this class, we'll really want to make sure that you understand layers 1 through 3. Put simply, layer 1 refers to the physical hardware. So let's give you some examples of things you might need to fix on the physical layer. Obviously, is the cable plugged in? For category cable, maybe you'd check to make sure it's pinned out correctly. Make sure there's no shorts in it. Make sure that as people pulled it through the conduit, they didn't pull too hard, making the cable thinner and changing the impedance characteristics. Make sure you don't have any electromagnetic interference that would overwhelm the signal in the cable. For optical cables, maybe you'd make sure there's no dirt on the ends. Make sure you're not going through too many passive junctions that might be leaking light, right? All of these things would be solved in the physical space. Now, layer 2 and up operate in the logical domain. A logical domain means we are working with logical concepts rather than the hardware you can touch. Layer 2 works with MAC addresses, while layer 3 works with IP addresses. Just to clean up the diagram a bit more, let's zoom in on those 2 layers. So layer 2 covers MAC addresses. As we've learned from our chapter on ARP requests, switching within our subnet happens by MAC address. So just think of this as switching in your VLAN. In that space, we have a wealth of protocols available so that we can move traffic efficiently. We can use unicast, multicast, and broadcast. So layer 3 refers to IP addresses. And IP addresses are used when moving traffic through a router to another network. So if you remember, when we need to contact a device outside of our subnet, we contact the gateway, we contact the router. Now, to be clear, the connection to the gateway is a layer 2 connection. But once we move through the router to another network, that's a layer 3 process. And as we remember, at layer 3, unicast is allowed, but multicast and broadcast do not pass the router. Now, this isn't an accident. This is intentional. This way, when your device joins a network by DHCP, and that sends out a broadcast message, that will stop at the router. It won't continue on to every other internet-connected device in the world, right? So, layer 2 is switching. Layer 3 is routing. Now, if we want to get traffic between VLANs, here's what we do. All devices in a particular VLAN should be grouped in the same subnet, and a different subnet would be used for each VLAN. Internally, the devices within each VLAN will communicate at layer 2. Then you can establish a router to link the 2 VLANs together. Traffic can move from one VLAN to the other, going through the router by unicast. The router will know what subnet is used in each VLAN, and it will move that packet to the right location. Now, your home router usually just knows about 2 networks. There's your home network, and there's the internet. However, a router can be informed about more than just 2 destinations. In fact, if we want to get really crazy, we could say that your LAN could have multiple subnets and many routers. By using multiple routers, you could design a system that would allow a packet to traverse a much larger network. So I remember when I first grasped this concept, I got how it worked, but then I had a thought. Why would I break a network into VLANs just to reconnect them with routers? It seemed like busy work, you know? So let's put this in terms that non-IT people might understand. In hotels, large offices, convention centers, and the like, you may come across meeting spaces with air walls. If you want a larger space, we remove the air walls. And if you want to break them up, then we move the air walls in. All right, so a switch with no VLANs would be the one big room. When we close the air wall and break it up, that's like creating VLANs. Of course, if we wanted completely separate networks, then we're totally fine. But if we wanted to allow some connectivity between VLANs, that's like the hallway outside acting as a router, allowing people to move between the rooms. Now, this analogy seems so obvious in a meeting space, and yet when we apply it back to the network, it might not be sitting well just yet, because we haven't really talked about the purpose of the air wall. So what is the purpose of the air wall? Now, some people would say, it allows me to have 2 meetings. Okay. Allow me to be obtuse for just a moment and suggest you could have 2 meetings in this space with the air wall open. Could do it. The air wall doesn't increase capacity of the room or anything like that, right? What's the point of the air wall? Well, if you think about it for a while, you'll say it gives us privacy and it cuts down on noise between the rooms, right? I'm not going to get distracted by the meeting that's going on next door. Now I think we're on to something. So you'll remember that the layer 2 space can use multicast and broadcast, but layer 3 only uses unicast, right? When we explain multicast and broadcast messages, maybe we do a disservice by only showing a few devices. Now we do that because it makes it easier to see how the protocol works, but we don't necessarily see the downside of multicast and broadcast in certain circumstances. What happens if we scale this up? Here, we can see just how much extra traffic we might generate with broadcast or unmanaged multicast. And as the number of devices in our VLAN grows, we need even more of these messages to get our basic network functionality established. Our ARP tables grow longer, which takes longer to search. It all just becomes more overhead. Over time, we could imagine this would be cumbersome. By breaking a network into VLANs, we reduce the amount of devices affected by these messages. In fact, you may hear someone use the term broadcast domain. A broadcast domain essentially refers to all of the devices you can reach with the broadcast messages. Basically, everything in your contiguous VLAN. So, if you hear someone talk about segmenting the broadcast domain, they're talking about breaking these devices into VLANs, possibly to control the chatter between devices. So how many devices can I put in a VLAN before we run into trouble? Honestly, that depends largely on your network design, the types of devices that you're putting in there, how traffic will move between them, things like that. But it's safe to say that a 24-bit subnet is very popular. That gets you 254 addresses that you can work with within that range. That's a pretty good number. Now, if you had 300 devices, could you open up the subnet and make that work? Sure. But at some point, you want to start thinking about breaking things out. Okay, so the last topic for this chapter, we said switching is layer 2, right? So what exactly is a layer 3 switch? Well, routers are layer 3, right? To link VLANs together, we could use a separate hardware router, but what if the network switch had some routing capabilities built in? And voila! You have now imagined a layer 3 switch. Now there are different types of routing. I don't want to get bogged down in this video, but let's say there are small and medium business layer 3 switches that might be able to do simple routing between VLANs, but they can't create the firewall that you would use for an internet connection. You may still need a hardware router for that element. However, by using the inner VLAN routing inside your switch, you might actually get faster switching, and you would put less strain on your trunk lines. By being able to handle everything in the same box, you save yourself the effort of going across a trunk line to a router just to come back inside the same switch. All right, so this chapter involved a number of key concepts. Let's summarize them. The OSI model is a conceptual model for visualizing network communication. When we have our network engineering hat on, we'll primarily be considering layers 1 through 3. Layer 1 simply refers to hardware, the switch itself, the electrical or light signals going through the cables, that sort of thing. Layer 2 centers around the MAC address and covers switching within a subnet. Layer 3 refers to IP addresses and getting traffic across a router. We can take a network and break it into multiple VLANs. This can help isolate unrelated systems to their own spaces and reduce the chatter of network overhead. All the devices in a single VLAN should receive IP addresses in a common subnet. Different subnets should be used for each VLAN. To allow traffic to move between VLANs, we can use a router. And of course, while we know switching occurs at layer 2, there are such things as a layer 3 switch. That just means it has routing capability built in.